Hello. So let me begin this lecture by a summary of what we did in the last lecture. So number one is we elaborated on the temperature coefficient of resistance. We had seen that though there are electrons available in the circuit by their being very much there, the free electrons in the conductors, in order to make the current flow, I need a mechanism by which you push these electrons in the same way as the water is pushed in a pipe, and that is job done by the battery. So battery is the one which is pushing the electrons in the circuit, and as we had said, battery works like a pump. So which, according to our convention, pushes the positive charge. Actually what it does is exactly the opposite, but on the other hand that has been our discussion. So what the battery actually does is to take the positive charge carriers and it pushes them from a lower potential to a higher potential. I repeat once again that I always talk about positive charge carriers, though the natural charge carriers are electrons. So all that means is the direction of the electron flow is opposite to the direction of conventional current. So these positive charge carriers, when they are raised to a higher potential, and that is the job of the battery, in the external circuit they can just flow down the potential. So that is what it does. After that, we defined something known as electromotive force, which is a characteristic of our battery. And we said that electromotive force, and I repeat that electromotive force is not a force. It's an unfortunate nomenclature, but that's the way it is, because it was thought to be a force because apparently something was pushing these charges, but the name has stuck. So basically the electromotive force was defined as work done on that positive charge, work done on a unit positive charge in taking it from a lower potential to the higher potential. So our definition is electromotive force, which is usually represented by a script E, is dW by dQ. And you can see, since numerator has the dimension of work, so which is in joules, and denominator is in charge, which is coulomb, and that is the definition of a volt. Now, if you look at this definition, there is another thing that becomes clear, that since I know that the work in taking a charge by a vector distance dl is given like F dot dl. This is just the standard definition of work in terms of the force. F dot dl, F is the force. And remember that my electric field E, so this is my force, and so therefore I can write my EMF as equal to, if you like, integral of F by Q, because we said that it is per unit charge dotted with dl. That's the definition of this thing. Now let's look at this definition a little more carefully. Now this is from the lower potential to the higher potential. So let me draw the standard battery. So that's the way it is, the battery. So the electric charges are being taken, positive charges are being pushed from here to there. And after that, of course, in the external circuit they can flow. But if you look up this expression, very frequently we write the electromotive force in a slightly different way. We write this as integral of E dot dl. Because we are talking about electric field, which is nothing but the force per unit charge, and what you will find is that your definitions will also have a circle around that integral, meaning thereby this is called a contour integral. Meaning thereby that you take the line integral of the electric field, this is a line integral as you are aware, around a closed loop. Now how does it work? How do I show that these two things are equivalent? Now look at it this way, that when I am, if you like the word, pushing the positive charge from here to there, this is happening by the chemical reactions driving them. So this force, if you like, is a non-conservative force. So inside the battery, the force is non-conservative. Now outside everything is, nothing changes really. You have to, of course, say that once the transient currents are gone, I mean everything is time independent. So outside the field is electrostatic field. So field outside by definition, electrostatic field, as you have learned, is a conservative field. So therefore my force has two components. One is that there is a conservative part, or electrostatic part, which is outside, and a non-conservative part, which is inside. Now I also know for the conservative part, integral F dot dl is equal to 0. And that is because by definition of a conservative force, the work done is independent of the path between any 2 points. So if you are going back from one point to another point, you can go by any path. But if you return back to the same point, then the work done has to be 0. So if I look at conservative dot dl, it's equal to 0. That's not true, of course, of non-conservative. But you remember that my non-conservative force outside the battery is 0. So therefore, if I add up these, that is outside the battery I add a non-conservative, inside the battery I add a conservative part which was 0, but I add it anyway. Outside I add the non-conservative part, and non-conservative part is 0, so I can do that. So therefore, if you add them together, you get a definition like EMF is given by, because per unit charge, contour integral, closed integral of E20. And that's the reason why EMF is frequently defined like this. And we will have more to say about it when we discuss the definition of the electromagnetic force in connection with Faraday's law of induction. But this is the way it works. Having done this, what we did is to summarize what happens for ohmic conductors. We had seen that the current density is related to the electric field by J equal to sigma E, where sigma is the conductivity. The current itself, which is J dot A, is the area vector, this is the current density. So this is given by E A by rho, and that's equal to your V by L is the electric field. I have a rho there and an A there. So therefore I get an alternative relationship which says V is equal to IR, because R is nothing but L rho over A. So any of these relations you have for the ohmic conductors, J equal to sigma E, then or E equal to J rho, and V equal to IR, etc. A constant electromotive force, namely a battery which has no internal resistance. Now, normal batteries have some internal resistance because you cannot eliminate material elements and they always offer resistance. So firstly, an ideal EMF source, an ideal battery if you like, provides a constant voltage across its two terminals. So let me draw a very simple circuit, and later on maybe I will do a little more complicated circuit. So this is my source of EMF, and I put a little resistance there. I will explain why. And there is a resistance in the outer circuit. So what happens is this, that this is my seat of EMF. What is frequently done in electric circuits is to do this type of a mark with a little circle at the base to indicate I am talking about EMF direction, that is the direction in which the voltage increases from negative terminal to the positive terminals, and there is a little internal resistance there. So this is your representation of the battery. The outside circuit RL, this is what is known as a load resistance, because that is the load that the circuit bears. So the rule is something like this, that supposing you go in the direction of current. So let me just quickly try to write this somewhere here. Going in the direction of current, as you go through a resistance, the potential drops by an amount R, AIR. That's rule number 1. The second rule is, if you move from the negative terminal to the positive terminal of a battery, then you increase the potential by an amount given by the EMF. So, in going from negative to positive, delta V increases by E. Okay, with that idea, let us try to see how does the potential vary in this case. Let us look at the following circuit. So I have a battery here, and this represents its internal resistance, and a load resistance which I will write as RL. Let us look at the current in this circuit. Supposing I go in the direction of current, going from the point A to point B. Say this is likely to be the direction of the current because the positive terminal is on this side. So when I go from A to B, there is no drop. So the potential at the point B is the same as the potential at the point A. But since I am going in the direction of current, in going from B to this point C, let's say, potential would drop from B to C by I times RL, where I is the current in the circuit. Then I get into this part where the source of EMF has also an internal resistance smaller. So if from C I come to this point, just cross the internal resistance, which is a representation, from C to D, it drops by I times small r. And then as I go from the negative terminal of the battery to the positive terminal, then through the battery, potential rises by E. So what have we got? We have said then, now when I do that, I return back to the point A. So in other words, if I go from A to B through C, D and back to A, this is what happens. So in other words, I get minus I RL minus I R plus E equal to 0. So which gives me I is equal to E divided by R plus RL. For definitiveness, let me take E to be equal to 10 volts, the internal resistance to be 3 ohms, and the load resistance to be 17 ohms. 3 ohms is rather a large internal resistance. The current in that case will be 10 divided by 17 plus 3. So that's equal to 0.5 amperes. Now let's look at how does the potential change. So look at this, that suppose I am going from A to B. Since we have already seen how the potential varies, so start at the point A and let me look at the potential at various points D, C and B. So I start with the point A, which is obviously at a 10 volt potential. Now, when I cross over to the point D, now since the point D is connected to the negative terminal of the battery, the potential comes to the value of the negative terminal, value it has in the negative terminal. I don't know exactly how the potential changes inside the battery. So let me just draw it by a dotted line. Now, having done that, I go from point D to the point C through the resistance small r. Now, there, since the resistances have been assumed to be ohmic, the change in potential would be linear as it goes through the resistance. So therefore, from D, it sort of rises as I go to the point C, or rather the end point here. And this rise, not to scale, but this rise is, current I is 0.5, R is 3, so therefore this rise is 1.5 volts. Now, having done that, I remain the same, the potential remains the same up to this point, and then again when it crosses the RL, it rises coming back to the value 10 once more. So this is, if you like, the point B, which is obviously the same as the point A. So let's look at it a little more clearly. So what I have said is this, that there is a method which you can adopt. Now remember, towards the end of last lecture, I had started talking about how to analyze a circuit having two batteries. So I am going to bring it back and redo the problem with this pictorial representation of the voltage drop. That gives you an idea of how one sees the voltage drops. So let me repeat that circuit again. So here I have got two batteries. Let me say that the first battery is like this, and this has an internal resistance of R1, which is 1 ohm, and this is E1, which is 2 volts. And then I have another battery whose polarities are like this, having an internal resistance of R2, which I take it to be 1.5 ohms, and E2, which is taken to be 4 volts. And then I have the external circuit where I have a load resistance, which I take it to be 5.5 ohms. So let us look at, in this situation, what actually happens. So let's start from some point. It doesn't matter where you start. So let me start from this point A, let's say. Now, in principle, I really don't need to know what is the direction of the current. But let us suppose, just for convenience, I am going like this. Why am I going like this? Very simple. By looking at this figure, that this is a 4 volt battery, this is a 2 volt battery, I realize that the net current is likely to be like this. So I am going in the direction of current. So let me look at that. If I am going in the direction of current like this, and I am going from A, this point A, and let us suppose there is a point which I mark as H, then I will do the following calculation. I will say V of at H is equal to V at point A minus E1, because I am going from positive terminal to the negative terminal. So minus 2, if you like, because 2 volt was that. Having done that, let's go to another point across the internal resistance. Let's call this point G. Now what about Vg? Now we have said if you are going in the direction of current, then potential would drop by an amount I times R. So therefore, Vg is equal to Vh minus I times R1, which is equal to Vh is Va minus 2 minus I times 1 ohm. So let's write it as I times R1. Now of course, what I could do is to calculate what happens to the current, how much is the current, exactly the same way. What I can do is go from here to there, there to there, there to there, and come back to it. So if I do that, all that happens is I drop a potential 2, increase by I times R1, increase by I times 5.5, increase by I times 1.5, and then increase by 4. So therefore, what happens is this, that my result is my current I then would be given by, I had increased by 4, this was decreased by 2, so this would be equal to 1 plus 5.5 plus 1.5, which is simply equal to 1 by 4 amperes. Okay. So how much is this? This is Va minus 2, R1 is 1 ohm, so therefore 1 into 1 by 4, which is 0.25, and that is Vg. But then Vg is also equal to, I am going by this E, because there is nothing in between, these are resistanceless wire, so this is identical to Ve. Now let me come to this point, D. So we say that Vd is Ve minus I times 5.5, that's equal to Ve, I was taken to be 1 by 4, shown to be 1 by 4, 5.5 into 1 by 4, which is 1.375. And if you look at this relationship there, so I have got Ve equal to Va minus 1.75. So this gives you Va minus 3.625. And that is the same as the point B. Now, what I now need is this. From B, I come to the point C. So my Vc is Vb minus 1.5 times I is 1 by 4, which is equal to Vb minus 0.325, and that's equal to Va minus 4. So that gives you the difference between these 2 points, that is Vc and Va. Vc and Va, this is the way it is. And then of course, if you want to come back to A, then you increase the potential by 4, so you are back to A. So this essentially tells you how the potential drops are to be calculated. Now here I assumed a priori that current is in that direction. You don't really need to know what is the direction of current. Suppose you did not and you assume opposite. So when you go opposite to the direction of current, then of course as you go through a resistance, we have seen that the potential will rise. So go exactly like this and come back to the same point. if you do that, you will essentially have the same calculation, excepting that what was happening here was when I went from here to there, my potential is dropping here, increasing there. But instead of that, this will, I'm going from positive to negative here, so therefore the potential will drop there, but increase here. So my current would still turn out to be the same in magnitude, but it will show up with a negative sign. So therefore, I know my original assumption regarding the direction of current was wrong, and I should come back and do it correctly. So this is the way you look at the variation of potential as you go through a resistor. So basically all that I have said is that when a current passes through a resistance, this is very important. When a current passes through a resistance, in going from higher potential to the lower potential, the drop is I times R. Now, having done that, let me look at another job that the battery is doing. So we have said that the job of the battery is to push or lift a charged particle, the positively charged particle, from lower potential to the higher potential. Now, so since it is the amount of work that is done on charge, so this amount of charge, in order to push it, the I, meaning thereby the battery, will have to do some work. And this work that the battery does is obviously because of my definition of the EMF. I can calculate it easily because EMF was work done per unit charge. So therefore, the amount of work done is the amount of charge that you take to a higher potential. So the work done will then become the EMF multiplied by the charge. And this amount of work obviously gets delivered, or this amount of work is done by the source, which is the battery. And once the positive charge comes to the higher potential, it can flow in the external circuit. In other words, in terms of the energy, whatever its energy was, it can now be spent. This is the amount of energy that is being supplied to the external circuit. So let us look at what is the amount of power delivered by the circuit. So that, let's call this P of the battery, which I call it as PEMF. So that's equal to dW by dt, the work done per unit time. But dW is nothing but the EMF times dq, that's the amount of charge that has been lifted through this potential barrier, and by dt. But if you recall, dq by dt is nothing but the current, so it is E times I. So this amount of energy is delivered by the battery to the external circuit. And so therefore, this amount of energy has to appear as the internal energy of different parts of the circuit, which could be electric field energy, mechanical energy in case there is a motor or some such thing in the circuit. If there is a bulb in the circuit, it can be used to light it up, or simply heat up the resistance. In the case where the energy is dissipated by the way of resistor getting heated, This is known as the joule heat loss. This is the amount dissipated by amount of energy which a resistor absorbs and dissipates. Now, in the case, I have a very simple circuit. Supposing we simply have a circuit like this. I just have a ideal battery. This is plus, this is minus E, and let us say I just have a resistance. Let's call it just the load resistance, RL. This is a point A, this is a point B, no internal resistance. And looking at this direction, this is a positive terminal. So therefore, VA is greater than VB. So if a charge dq comes from this terminal to the point A, okay, the potential energy of that charge is VA times dq, and at B it is VB times dq. So what has happened is, there has been a change in the potential energy. And normally we define change as final value minus the initial value. So therefore, the change in the potential energy, let's call it du, that's equal to dq times final potential minus the initial potential. And let's call this delta V. So therefore, my du by dt, that's the rate at which the energy transfer takes place, is dq by dt times delta V, and that's equal to, now dq by dt is I, so the current times delta V. Now if Ohm's law is valid, then I is delta V is I times R. So that therefore the power is I square R. And since I have a simple circuit, I is equal to V by R, so therefore this is equal to V square by R. So let's look at what is this happening to this energy. Now when this energy goes through the resistance, now we know that it should result in an increase in the kinetic energy of the charges because of the work energy theorem. In other words, these charges should accelerate. But remember what we said. We said that the charges in a conductor actually accelerates, but that's a very nominal situation because they keep on colliding and move with an average drift velocity. So what has happened to this increased potential energy that we have given it to charges because of the work done by the battery? So what has increased is this, that this increase in the energy gets used up in collision with atoms. So electrons collect additional kinetic energy, collide with the atoms, and as a result, they transfer energy to these atoms. Now this makes the atoms vibrate more rapidly because they have now got some kinetic energy. Now this will result in an increase in the temperature of the resistor. So this results in increase in the temperature. Now I would like to give you an example, a similarity. Now in your mechanics course, you have always learnt about the when you drop a mass through a viscous liquid. You have heard about that it attains terminal velocity. Now remember that since it is falling under gravity, though there are viscous forces also, it is reducing its potential energy. Now if it is reducing its potential energy but still moving with an uniform kinetic energy, uniform velocity, then this loss in the potential energy appears as a internal energy of supposing you have dropped a stone, that liquid or whatever. But that would generally result in an increase in the temperature. We don't normally measure such increase in temperature because the amount is somewhat low. In case of a resistor, if a current passes through it, because of this reason, because of the energy that is being transferred from the battery to the resistor will get heated up. Resistor gets heated up and it radiates heat. It would become hotter to touch. And also if there is, for instance, a bulb in the circuit, it can be used to light it up. Normally, these are laboratory situations. But you see, we also have generating stations which actually generate electricity, just as battery is doing it in a small scale, and supply it to various cities. And there are usually large distances between the generating station, which are normally not located inside the city, and the place where they are being transported over large distances. Now, over large distances, when you transport electrical energy, that is carrying current, you have a power loss. So this is equal to I square times R of the wires. And remember that these wires are over large distances. So this is equal to P square over V square times R. So what happens is this, that if you want to reduce the power loss, you would like to transport it at very high voltage. Because if V is large, then the loss during transmission will be small. But that makes the whole process unsafe, because you are supplying energy at transporting electricity at high voltage. So it is, and it's unsafe. So it is necessary that at the consumer's end, they are the voltage is reduced using what are known as step-down transformers. So let me now talk about, or give you some examples of how this power thing works. So let's first start with a simple circuit. So in this simple circuit I have taken, supposing I have a resistor of length L, cross sectional radius R, resistivity rho, etc. And supposing I have a 18 volts battery. And it is given that this resistor absorbs 80 watts of power from the source. Now my question is this, that supposing this resistance wire, you take it out and draw it to another resistance uniformly, which has 4 times length. Now then what statement can I make about how much of power is absorbed from the source? This is the question. So what we have given is this. Let's first write down what is the resistance like. So resistance, as you know, is rho times the length L divided by pi r square. The current, as you know, is V by R. So what we have said is this, that this absorbs 80 watts of power. Now when you draw it to 4 times its length, now remember the volume had to remain the same. If the volume remains the same, it means the cross-sectional area has also reduced by a factor of 4. But the resistance, which is proportional to length, which has increased by a factor of 4, and inversely proportional to the cross-sectional radius, which in this case has decreased by a factor of 4. So the net resistance in the process has increased by a factor of 16. So my R prime is 16 times R. So how much is V square by R prime? This is my power. So V square by R prime is V square by 16 times R. But V square by R is given to be 80 watts by 16. So therefore, that this situation, it will absorb 5 watts of power. Look at the current in this situation. Now, if you look at the current, since the voltage is 18 volts, I have V by R prime, V is 18 divided by 16R, but 18 by R was my original current I, so it is I by 16. So I square R prime, if you want to calculate, is equal to I square by 16 square, which is 256, times R prime, which is 16R. That's equal to I square R by 16 as expected. Now the question is this, that what frequently confuses people is that which formula do I use? Is power V times I? Or since I is V by R, is it V square by R? Or is it, since V is IR, is it I square? Now you would say they are all the same. Now they are all the same, provided all that you have is a single source of voltage, that's an EMF source, and a single resistance. Now look at what difference does it make. So I'll give you a small example. So let's look at this situation. This is potential drop is V. Whatever I have done here is right. No problem. All the three formulae are the same. But suppose I have a slightly different problem. I have a 100-volt source. There are three resistances there. 5 ohms, 8 ohms, 7 ohms. You see what is happening in this situation. Let me first calculate how much current I have. My current is 100 divided by 5 plus 8 plus 7, which is simply 5 amperes. So the power that is delivered by this source is given by this formula. So power delivered by two circuit, this is equal to 100 into 5, which is equal to 500 watts, of course. But let's look at what happens here. Here it is I square R. The reason is, if you want to use the other formula, you must then find out what is the potential drop across this point, not this 100. But if you say what is the current, because the current is the same in the whole entire circuit, then you can do I square R. So how much is I square R for this? This is, the current is 5, so it is 5 square, which is 25 times 5. So this is giving out 125 watt. This one, 25 into 8, that's consuming 200 watts. This is 25 into 7, that's consuming 175 watts. If you do the arithmetic, you find this plus this plus this is 500 as expected. So what we are saying is that when you use this formula, be a little careful. The V in this formula is the potential drop across the resistor that you are talking about, not the potential supplied by the battery. I square R is always correct provided that is the current passing through this resistor. You have to be careful if it is not a simple circuit like this, because there various parts of the circuit may have different amounts of current. So this explains what actually we need to use. So let me quickly tell you what we have achieved today. We have said that the seat of EMF lifts positive charges from a lower potential to the higher potential, as a result of which the battery does work on these charges. This charge that the battery does is equivalent to an amount of energy which is available to the external circuit. And this energy that we have got, if they are passing through resistances or other components, they can be used to do either useful work, like for example turning a motor, or simply gets dissipated, as happens when you use it. For example, just the resistor dissipates the heat. So this is, we will continue with the power and some more examples we will give you in the next lecture, and after that we will go to a discussion of circuit principles.